In the last video, we did a construction where we copied the three sides of a triangle onto a different triangle. And I said that this was going to change the way we thought about congruence from just being the same size and shape. We're going to use a more formal definition from here and starting forward. So let's talk about what that is. We talked last week or the week before about rigid transformations. There were three of them. Remember what they are? There's translations, reflections, and rotations. And when we looked at each one of them, we saw that each one of those three rigid transformations preserved distance and angle size. And so any triangle that you may do in one of those three transformations, you would come up with a triangle that was congruent to the original triangle. Imagine for a second that we had a triangle and we did two rigid transformations to it. Okay, so I took my triangle and I translated it, and then I reflected it. After I did both of those steps, is that triangle still going to be congruent to the original one? Yeah, it is. Because this triangle is congruent to this one, the same size and shape, which is the same size and shape as this one. So yeah, there's nothing that changes from here to here. And so that's going to be the basis of our new definition of congruence. That two figures are congruent if there is some sequence of rigid transformations that transforms one to the other. Sometimes it can be done in one step, sometimes it needs more than one step. But either way, eventually you're going to be able to overlay the two on top of each other. Let's take a look at the triangles we made in the last video and see, based on this, if we can show that these two triangles are congruent to each other. So I've got a piece of parchment paper here. And what I'm going to do is I'm going to trace out my original triangle. It's just a little bit wobbly. All right, so there's A, there's C, there's B. All right. So let's do this sequence of rigid transformations. Let me translate this so that B is on top of B prime. All right, just pretty much like that. All right. So I need to give a starting and an ending point of one of my vertices to specify what a translation is. Now I want to do a rotation to make this line up a little bit better with that triangle. Can you imagine what I'm going to do here? Well, what I'm thinking is that when I do a rotation, I need to specify both a center point and some sort of angle. All right, so I want to rotate around point B. I want that to be my fixed point because I want B to stay on B prime. But I want A to get over here to where A prime is. So what I'm going to do is I'm going to rotate this around B clockwise by the size of this angle from A to B to A prime. And when I do that, okay, I am right there. All right, so I'm not laying on top of the image triangle quite yet, but can you see how close I am? What's my last step going to be? Remember that when you specify a rigid transformation, you've got to give it precisely. So it's not just enough to say that it's a reflection. You need to say, what do you need for a reflection? You need to talk about what line you're going to reflect across. And in this case, we want to reflect across this line that contains A prime and B prime. And so when we do that, we're just kind of flipping the paper over. And when we do that, yes, now our image lies completely on top of the image triangle that we came up with. So what we just showed is that using a sequence of rigid transformations, we started with a translation, then we did a rotation, and we wound up with a reflection. And that sequence of rigid transformation transformed this triangle into this triangle. And so based on the new definition we have, we can say that these two triangles are congruent. But think about for a second what we did to construct this triangle from this. We didn't know anything about the angles that made up this 3 triangle. We only copied the 3 side lengths from here. And so that's a really cool point, that if you only know the 3 sides of a triangle, if you created a triangle that had 3 given side lengths, let's say I told you to create a triangle that was 4 inches, 5 inches, and 6 inches, the lengths of the 3 sides. And I asked the person in the chair next to you to do the same thing. Is it possible that you're going to come up with 2 different triangles that aren't the same size and shape? Well, what we're seeing here is no, that's not going to happen. I made a few decisions when I created this over here. For instance, I called this B prime and this A prime. I could have switched those 2 letters. When I formed the point C prime, I formed it above the line. I could have found a point below the line. But any way I did that construction, and you can try doing that in all 4 different possible ways, you're going to see that there's some sequence of rigid transformation. Sometimes you need to do the reflection, sometimes you don't need to do the reflection. But either way, the 3 sides are enough to specify a single unique triangle up to that congruency definition. And so what we're going to call this idea is the SSS theorem. This is going to be something we go to over and over for the rest of the year. SSS stands for side, 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 because those were the 3 pieces of information I gave you about this triangle. I said, make a triangle that has the same side length as this, make a triangle that has the side length that's the same as this, and make a triangle that has the same side length, the same side length as this. Got them backwards because I reflected. And that is enough information to know that these 2 triangles are congruent to each other.